Well, guys, today we will talk about physical pendulum. Well, let us see what is physical pendulum. Now, suppose you have any rigid body and you make a hole and just suspend it through this hole with a nail. Then this is a physical pendulum. Anything. If you have a scale, make a hole and suspend it. This is a physical pendulum. Because if you push it, what will happen? If you push it and leave it, then this will start to and fro motion like this along with this axis where you have suspended it. So in this, any rigid body can be called a physical pendulum. So suppose this has a mass, or this is a center of mass. And the mass of the rigid body is m. Then, of course, it will have gravitational force. Likewise, it will have a normal reaction on this nail due to suspension of this. Basically, they both will be in the line. Let me draw it because in the equilibrium position, they have to be in the line. And your rigid body will keep on suspending like this, and this is called equilibrium position. Now suppose if you just push it and suppose your body is in this fashion and your center of mass is here. So what will happen? It will have a gravitational force. Of course, suppose this is the distance. This is the distance L between center of mass and suppose this point is M. Then what will happen? In the simple harmonic motion, in case of simple pendulum, we saw that there will be a restoring torque. So from where this torque is coming? In this case, suppose if you divide this force into two components along this line NC and perpendicular to the line. This is your mg sin theta, and what is this? mg cos theta. So mg cos theta will not develop any torque because it is in the line of this NC. This mg sin theta, it will develop a torque like this. mg sin theta into, of course, L. So this is the torque acting on this rigid body, which is making this rigid body to come to its equilibrium position. Again, as we saw in simple harmonic motion, in simple pendulum, this will not remain in the middle position. By inertia, it will go further. Correct? It will move like this and it will keep on moving like this. And this is called to and fro motion. So the same principle we had in simple pendulum case also. But this is not a simple harmonic motion. Of course, because here tau is equal to sin theta. Correct? But sin theta for small angular displacement. What is this angular displacement? This is of course theta. So this is the angular displacement for sin theta. For a small theta, it is sin theta is equal to theta only, and it will be nothing but your torque is nothing but proportional to theta. Of course, this is minus theta because it is the restoring torque. Mind it, because torque is acting like this, whereas when the motion is like this. So in the opposite direction, the torque is. So basically, this is called restoring torque. So this is a condition for simple harmonic motion, and torque is nothing but I alpha proportional to, or you can say, is equal to m g l into theta. Here alpha is, this is what? This is angular acceleration, correct? So this is basically proportional to theta, displacement, that is angular. So theta is nothing but mg l upon l, and that is equal to I. And in the simple harmonic motions, you see minus omega square theta. So here basically this is minus because of this minus, correct? So basically what is omega square? Omega square is nothing but mgl upon I, or omega is your root mg l upon I, correct? And what about omega? Omega is nothing but, this is your angular velocity, and this is nothing but 2 pi by t. So your t is again the same thing. Your t is nothing but 2 pi upon omega, correct? And this will be nothing but 2 pi root I upon mg. So in case of rigid bodies, time period is this. Of course, frequency is 1 by t. You can find out what is I. I is the moment of inertia of rigid body along with this axis where it is suspended, or where it is, from where it is executing an angular displacement or simple harmonic motion. So anything, any rigid body, it can be there, which is in scale, or anything, it can be there. You can have the moment of inertia, you can find out the time period. So this is also basically a case of simple harmonic motion. We will see what is torsional pendulum. Torsional pendulum is, you have a, suppose you have a, what is this? This is a disc. Now it is joined with this rod, and rod is suspended. So rod is there with this rigidly, actually this disc you have joined it, so it is not able to move. So in this case, actually what happens, suppose you give it an angular displacement. Suppose if you give an angular displacement, then what will happen? Since the rod is rigid, correct, it will have a torsion, and due to that torsion, it will have a restoring torque, correct? Now this restoring torque we have seen, suppose this is tau, this is nothing but I alpha, correct? And alpha is nothing but tau upon I. And this restoring torque is again proportional to angular displacement in such a way that this is minus k. What is this? K is nothing but called torsional constant. It depends on the material rigidity of the disc and the rod. Correct? So with this, if you see, if you write, this is minus k upon I theta and torque is proportional to minus theta. Again, this alpha or alpha is nothing but minus k upon I theta, and we can write is, and here omega square is nothing but k upon I, or omega root k upon I. Correct? And so if you know that k, that is torsional constant, and of course the moment of inertia of the disc. Then you can find out the time period of this. This will be nothing but omega is 2 pi by 3, or t is nothing but 2 pi root I upon k. So this is the time period of this rotating, or you can say to and fro motion, angular motion of this disc. So this is basically is known as torsional pendulum. Now let us do some question for this torsional pendulum. Question is before you, that is, this is a torsional pendulum and here is a disc. Mass of the disc is 200 gram and time period of this disc is 0.2 second, and radius of this disc is 5 centimeter. So we have to find out the torsional constant, that is K. Correct? So in the last lecture we saw that torsional constant, time period is nothing but 2 pi root I upon K. So of course K will be nothing but, if you just square it, and then this will be nothing but 4 pi r square I upon T. T you know from here, I you don't know. So what is I? I for the disc is nothing but m r square by 2, and this will be nothing but m is 0.2 kg into, of course, r is your 5 centimeter. So this will be nothing but 5.05 into square upon 2. We have converted this thing into meter. Correct? So this is coming as 2.5 into 10 raised to minus 4 kg. Correct? Now, what about T? T is given, so K will be nothing but torsional constant. That will be nothing but 4 into pi square into 2.4 into 10 raised to minus 4 upon 0.2. Correct? And of course, this will be, when you square it, this will be square. Correct? So what is the value? Torsional constant is nothing but 0.25 kg meter square upon, of course, second square. So this is how you can do the questions. We are going to take up for simple harmonic motion a lot of questions, because so far we have explained the theory part of it, but a lot of questions are there which in our coming lectures we are going to breakup.